Alright, hello SPH3U. This is video number 3. This one's about thermal energy. So first off, we're going to talk about temperature versus thermal energy versus heat. 3 related but very different physics concepts. We're going to talk about then the 3 methods of energy transfer, of thermal energy transfer specifically. Then we'll talk about the thermal energy of different materials that happen to be the same temperature, and the thermal energy of different states of matter that also happen to be the same temperature, so like ice at 0 degrees versus water at 0 degrees, and stuff like that. But first, a video. This is a YouTube video. If you want to watch this video in its entirety, just check the description. It'll be underneath all the timestamps. I've muted it for now because it's got really lame techno music, but you can enjoy that horrible techno music if you watch it yourself. And there's a reason that my face is in the middle here, because behind my face on this video is the temperature of the water. But what I'd like to talk about first is this. Keep in mind, our topic is not mutagens. Oops. Our current topic is temperature versus thermal energy versus heat. So the reason that my face is blocking the temperature reading is so that you don't know how hot the hot water is and how cold the cold water is, right? Hot and cold, what I'm trying to show here is that it's relative, right? Kind of like how in the spring, like a 7-degree day is warm and pleasant, and in the autumn, a 7-degree day is like, oh god, I need a jacket. Same thing here. Hot and cold is relative, so you don't actually know how hot this hot water is or how cold this cold water is, but on the infrared you can tell that this one is putting off more energy than this one. It's possible that this guy is like 30 degrees and this guy's like 60 degrees. We're going to watch them mix. Right? Oh well, suddenly now you see this person's hands, so you might get an idea of how hot this hot water is. Ooh, now we have an idea. Oh, and they tell you it's room temperature. The warm water gets poured in. And you can see the heat transfer right up here, right? You can see how the cold and the hot are kind of fighting up in the corner here. And you can watch it mix. So in this specific case, right, if I go back to the start here, right, the hot and the cold water. In this case, the middle ground was 22.9 degrees Celsius. But it didn't have to be, right? If I stick my face back in the corner, there's nothing in this image, aside from the person's hands, there's nothing in this image that tells you how hot or how cold the water is, just that one is hotter than the other. And you can imagine that if they were poured together, you'd get exactly the same kind of picture on the infrared, depending on how sensitive the camera was. If, maybe this guy here is at 0 degrees and this guy's at 30, maybe this guy here is at 30 degrees and this one's at 60. Or maybe this guy here is at 60 degrees and this one's at 90. You would still look exactly the same on the infrared. So that's the first lesson, and kind of the main point that I really want to hammer home here is that all objects have at least some thermal energy. All objects have at least some thermal energy. And then I guess there's a secondary keep in mind here, and that's that temperature decides the heat transfer, not amount of thermal energy. Right? Temperature is the thing that decides the heat transfer. It's not the amount of thermal energy. So, like, say this thing was 30 degrees and this is colder, this thing is going to transfer energy to the cold water. But if this was 30 degrees and there was like a 60 degree beaker of water, then the 30 degree one would get heat transferred into it. So that's the thing. It's things are relative. So let's watch that video again with my face out of the way this time. Back to where it normally lives, which is in the corner somewhere. And we'll watch this video and watch the heat transfer. Fun thing is to look at that hot spot left behind. Here we have cold water being poured into that mixture. You see that there's a patch of cold water and a patch of hot water that's left. And at the interface, there's going to be heat transfer between the two. And then eventually it's going to settle down. Yeah, infrared videos are super cool. Then here's a time lapse, so they're like running it in faster motion. You can see slowly it all kind of ends up the same heat as it mixes, you know, over time. So that's our introduction, right? That's our introduction. Let's jump over to the note, which is here. This is today's lesson, lesson 13, heat transfer and thermal energy. There's this old chemistry test question, but it works for physics as well. Imagine that you're holding a cup of boiling water, you know, maybe some tea, something like that, and you're on a boat in the ocean. Which object has more temperature? Right? Which one has the higher temperature? Is it the cup or the ocean? Well, I think it's obvious that the boiling water is 100 degrees Celsius and the ocean's like 10 degrees Celsius or whatever it would be. So yeah, the cup has more temperature. The cup has more temperature. Wow, that has more temperature. But which one has more thermal energy? And that's the one that trips people up. The cup is obviously a lot warmer, but there's a lot more water in the ocean. Like, a lot more water. And if you remember the point that I made at the very start of this video, all objects have at least some thermal energy. Well, the ocean, like a cup of ocean water, will have less thermal energy than that boiling cup of water. But when you're talking about trillions and trillions of cups of water in the ocean, I think overall the ocean's going to win. So the ocean contains more thermal energy than the cup, even though it's a colder temperature. It's an important distinction to make between temperature and thermal energy. Now, if you drop the cup of water into the ocean, which way would the heat flow? Well, we just watched that video of heat flowing. Heat always flows from hot to cold, so from higher temperature to lower temperature. So it would flow from the cup to the ocean. Right? The ocean's got billions of times more thermal energy, total thermal energy, than this cup. And yet the heat flows into the ocean, into the thing with more thermal energy, because it's a temperature difference. So heat follows temperature differences. And that's why there's this thing up here. Temperature decides the heat transfer, not the amount of thermal energy. So heat transfers from hot to cold. All right, hot to cold. From hot to cold. So that's our introductory little spiel about heat transfer and thermal energy. So let's talk about it. Let's talk about heat being the transfer of thermal energy. Here's a picture, or a GIF, I guess, of heat transfer, and you can kind of see in this temperature and thermal energy together. So this reaction, this chemical reaction, is turning chemical energy in the gas that it's burning into thermal energy. Right? We call that waste heat. And what it's doing is that thermal energy is making random wiggly motions in those particles. It's shaking up the particles. The more they shake, the higher their temperature. Right? Temperature is the average kinetic energy of each particle in the object. So once, when we look here, they're all kind of moving really quick. We take their average kinetic energy, and depending on their average kinetic energy, they're going to have a certain temperature. But thermal energy, total thermal energy, is the total amount of kinetic energy contained in those random motions. So, so that's what thermal energy is the total. Which is why the ocean can have more total thermal energy even though the temperature is smaller. There's just more particles to multiply that kinetic energy by. Now the conduction of heat, this is conduction, this is the easiest one to understand, is these ones are vibrating quickly, these ones aren't vibrating quickly, and so you get like a person standing still and then someone vibrating very quickly. And it's kind of like a mosh pit, right? This will start hitting this, and then they'll both start. This one will start vibrating slower, and this one will start vibrating quicker, and then together they'll start vibrating at a certain speed. So like this one starts really fast, and this one's normal, and then as they cut together, they're both now there's a transfer of energy between the particles, and then that'll hit the next one, that'll hit the next one, that'll hit the next one, and that's how heat conducts. So when we looked at this video, remember that hot spot that was left. That hot spot that was left by the warm beaker. That is from conduction. This thing was hot. It was jiggling, and so the tray underneath it was also jiggling, right? Because it was hot on top and it was jiggling, and then the tray started jiggling. And then they took this away, but the tray is still jiggling underneath, and that's why you see that hot spot just where that beaker used to be. So that's a conductive transfer of thermal energy. So that's temperature versus thermal energy versus heat. One interesting thing that you can do with this is to prove to yourself that humans don't actually feel temperature. We feel heat. We feel the transfer of thermal energy. And the easiest way to prove this is to find two objects, any two objects. My two objects are going to be here. First, an Xbox controller, Xbox 360. It's made out of plastic, so I'm holding it, and it feels cold. That's natural. It's been sitting here on my shelf for years. And is at room temperature. Meanwhile, my hands are at 37 degrees, so that feels colder than my hand. That makes sense. But my second object is a metal hole punch. It's made out of metal. And when I touch it, it feels colder than this. And that's weird, because they've both been sitting here for years. So this one should be the same temperature as this one. What I'm feeling is that this one can take thermal energy away from my hand better than this one can. These molecules are denser and more tightly packed. And my hand, the jiggly motion of my hand transfers into the metal easier than here. If you guys are sitting at a table or a desk, one of the fun things you can do is, if the desk is wood, you put one hand on the desk surface and one hand on the metal leg of the desk, and you'll get exactly the same feeling. And think to yourself, that desk, the leg and the wood are the same temperature, but you're feeling a different rate of heat transfer, right? So back to the note. If something transfers heat away from us, we feel cold. We feel that the object is cold. If something transfers heat into us, we feel that the object is warm. This is why water feels colder than air at the same temperature. Right? If you're in air at 21 degrees Celsius at room temperature and you feel fine, but if you jump into water at 21 degrees Celsius, it feels cold. Same thing for like saunas. A typical sauna is like 80 degrees Celsius. So you sit in there and you feel kind of warm. But you wouldn't want to jump into a pool that's 80 degrees Celsius. That's like hot enough to burn you. because the water is faster, better at hitting, the particles are closer together, so they're hitting you faster, so they'll transfer the energy faster. Heat transfer is affected by temperature difference, so a bigger difference changes the speed, but it's more dependent on the type of heat transfer. So that's our next topic, the three methods of heat transfer. So the three methods of heat transfer. All right, three methods of heat transfer. Wow, I cannot type today. Transfer. There we go. Heat transfer. And to keep in mind here is anything that can change the wiggly motion, I guess the random motion of particles can transfer heat. So anything that can change the random motion of particles can transfer heat. So that's now we're in our second thing, the three methods of heat transfer. So let's jump into that. Here are the three methods. They are conduction, convection, and radiation, and this is it. These are the only methods that heat can get transferred by. We already mentioned conduction. That's the easiest one to understand. You know, if I have this marker, which is also at room temperature, and I grab it with my hand, it feels cold. And it feels cold because my hand's particles are moving faster than the marker's particles. And so slowly, because they're bumping into the particles on the marker will heat up, and if I hold this long enough, the marker in my hand will get to be the same temperature, and then it won't feel cold anymore. So that's conduction. Same thing happens if you touch a hot stove or a hot pot. It's moving really fast, and then if you touch it, the particles are gonna bump into your finger, and then your finger particles are going to try to move really fast, and that's how you get a burn, because they start moving too fast and they kind of start ripping each other apart. So that's how you get a burn if you touch something hot. But that's not the only method of heat transfer. Conduction is the easiest one to understand, but there's two more. So here's conduction, right? You see that these are moving faster than these, and so it slowly conducts. Convection is a little bit harder to understand. Convection is a hot fluid moving, and fluid is an interesting word here. So I should probably add that in here, that a fluid can be a gas or a liquid. Right? A fluid just means something that can flow, right? Like you can actually see the word kind of flow in there. Fluid is flow, so gas or liquid moving. So the best example here is a shower, right? I'm upstairs. My shower is actually behind that wall. But the hot water tank, where the water actually gets hot, is 2 floors down in my basement. So when I turn on the shower, it takes a little bit of time for the water to heat up. But it's not like it's heating up at the shower head, right? It's heating up in the hot water tank. How does that heat get to me? Well, it's stored as a big bunch of hot water in my hot water tank, and then there's a pipe that brings that hot water up to me in my shower. So thermal energy has been transferred from my basement to my second floor where I'm taking my shower, but it wasn't through conduction, right? Imagine waiting for water to heat up through conduction in a pipe when you're taking a shower. You know, like almost like there might be like a door, and then it opens up, and now the hot water is touching cold water, and you got to wait for that heat to slowly propagate all the way up to the second floor. Yeah, no, that's too long. Instead, you actually push the hot water over, and the cold water gets replaced with hot water, and now you've got hot water. So convection is the movement of a hot fluid. We see the same thing in like weather reports and stuff like that. So, you know, if I pull up, say, weather system map Canada, you know, here's our system map. you can see that there's kind of hot air down here and cold air up here, and you can see that the cold air right now is moving downwards and the hot air here is moving towards the east. So like tomorrow, this hot air is going to be over here where Ottawa is, and we're going to have a warmer day tomorrow than we will today. So convection is what's responsible for our weather changing a lot of the time. A lot of the temperature changes in, especially at this time of year when it's like cold one day and hot the next. When it's cold, that means cold air from the Arctic has pushed down. It got cold up in the Arctic, but now it's down here. And then when it's a warm day, it's hot air from the States that has pushed up, and now it's warm because that air got hot down here in like Oklahoma and Texas and stuff, and now it's up here in Ontario, giving us its nice thermal energy. So that's convection. Convection is the movement of a hot fluid, a hot thing. The last piece is radiation. So radiation. Radiation is kind of a weird one to explain. Let me just get my oop, that's not what I want to push. This one's what I want to push. There we go. Basically, radiation is interesting. You can imagine it like, imagine having your hand on top of some water and you're pushing up and down. If your hand is pushing up and down, the water around your hand is going to push up and down in a wave and then spread out. And the faster you push your hand up and down, the more energy goes into that wave that's spreading out. All right? That's what radiation looks like, except for what's pushing up and down isn't your hand, it's the charges that are in everything. Like everything is protons and electrons. So when they move up and down, their charges are moving up and down. And that is pushing up and down on what we call the electromagnetic field, and that's splashing out as electromagnetic radiation. And that's how radiation works. Literally everything radiates. Everything radiates. Everything radiates. Right? Everything. Everything radiates. And the warmer you are, the more you radiate. So, right now I am radiating more thermal energy than the rest of this room because I am warmer. My particles are moving faster, so those waves that are coming off of me, those infrared waves in the electromagnetic spectrum, are higher energy and leaving from me in all directions. That's how infrared cameras work. So I'm going to pause the video for a second, find an infrared camera video, and we'll use that to explain the radiation thing. Because since I'm radiating higher wavelength, higher frequencies, higher energies than the rest of the room, I am glowing in the infrared compared to the rest of the room. So I'm going to pause and find that video, and I'll be back in no time for you. Okay, so I found a great one that's called Mouse Can't Hide from Infrared Camera. So again, everything radiates. Every single thing radiates, and warmer objects radiate higher frequency. And because it's a higher frequency, a camera can be tuned to that specific frequency and see that object. And those frequencies can go through other objects because it's almost like light, right? This is a plastic bag back here. You know how sometimes plastic bags you can see like a little bit of light through them? That same thing, the infrared's going to go through the plastic bag. So let's watch this video and you'll see that the mouse is hotter than the surroundings, and so the camera is going to be able to see it even though it's behind the bag. And again, the full video is going to be down in the description if you want to watch it again. So yeah, the full the heat of the mouse, the infrared rays are going right through the bag and hitting the camera, and so the camera can see right where the mouse is because the rest of the bag isn't radiating nearly as strongly as the mouse is. The rest of the bag is still radiating, that's why it's purple, but the mouse stands out because it's radiating at a higher frequency. One neat thing is you can actually see the crinkles in the bag because those rays are kind of coming through those crinkles and bending as they're coming through the crinkles. Kind of like when you have like that wavy glass privacy window stuff where all the light kind of gets messed up as it's coming through. Crinkles in the bag will actually deflect the infrared ray as well. So it really is very much a light wave that's passing, except for the light wave is invisible to humans, so we need special cameras to see it. So that's radiation. Everything radiates, and it went right through the bag. It's light. Anything that, a lot of the same things that light can travel through, infrared radiation can travel through. So like, like a window, infrared radiation will go through a window, it'll go through the air, it'll go through space. So this is actually how the sun gives us its energy. Right? This is a cool graph of the hotter the temperature, the lower the wavelength is going down, and the more total energy gets radiated as well. So because radiation is basically just a light wave, it can travel through space. It can travel from the sun all the way to us. None of the other ones can. So like there's no particles in space for the jiggly motion of the sun to touch another particle and another particle and another particle on the way to us. So that's not going to work. And in order for convection to work, like a chunk of sun fluid needs to come over to the Earth and deposit its energy. And I mean that happens sometimes with solar flares and stuff, but not enough to keep life alive here on Earth. So really the vast majority of thermal energy from the sun is brought to Earth by radiation. Right? And you can actually a campfire is a good example of all three. If you tried to touch the campfire, like the actual logs themselves, you would get burned by conduction because the logs are jiggling very fast, and so it would make your hand jiggle really fast, and then you would get burned. The air, this is making hot air, and that hot air is going to rise. So if you put your hand above the campfire, the hot air rising is going to bring hot air up and burn your hand from the hot air. Interestingly, that burn still happens from conduction, but the heat got there from the fire by convection. And then the last piece is if you have your hand next to the fire, you don't even have to be above the fire where the hot air is going or touching the fire. Just the infrared will actually come in and hit it's a wave. And just like in a wave pool, if you're in the wave pool, you go up and down with the wave. When there's something vibrating and making radiation, it's making that wave. So it's making that wave, and this thing's going to follow that wave like it's in a wave pool with a little bit of like a speed of light delay. So this thing can start not moving, but if this thing is moving, eventually this thing will start moving too. This is how microwaves heat up your food. It's through radiation. So you're irradiating your food every time you use a microwave. It's kind of interesting. All right. Then let's talk about preventing this thermal energy transfer. If we can stop conduction very easily, right? Like if there's a hot object and I'm touching it, how do I stop heat transfer from conduction? Well, I just stop touching the object, because it requires the two particles to be right next to each other and like mosh pitting into each other, right? So if you go like this and this guy's going nuts, and this one's like, dude, what are you doing, right? There's no impact, there's no collisions, so you just stop touching it. right? And this is often done with just layers of air because air has the particles spread really far out. So like this one can move, but this one won't move, or it'll take a while for this one to start moving. And usually it's like coats and stuff, so like layers of air with walls between them so that it takes a while. I've got a really good example of that, so I'm going to find this video for you guys, just a sec. Okay, so this is the Space Shuttle thermal tiles. The Space Shuttle is no longer running, but they still do this demonstration at NASA. I'm going to change actually the heat transfer. Right, the current topic is preventing heat transfer. So what's going to happen is this is a big oven, and out is going to come a thermal tile that is glowing white hot. So there's the thermal tile, glowing white hot. And this stuff is made out of basically, like, imagine styrofoam, because it kind of looks like styrofoam, except for it's a ceramic. So it's like there's a bunch of air gaps there, right? Like how styrofoam has air between it. And this person can just kind of grab it and touch it by the corners, because there's so much air in those thermal tiles that also you can see where the tile used to be because of the hot spot, which I always think is really interesting there too. It's very, very cool. So yeah, they can prevent the conduction because there's so many air pockets there. This is also why you can get those styrofoam coffee cups that are terrible for the environment but really good for keeping something warm. Once again, this video down in the description if you want to see it again. So back to this. Interesting. So foam insulation. This is why our houses have like insulation, fiberglass insulation. It traps air, and so the air is trapped in the fiberglass insulation. And the thicker the insulation, the better the prevention of conduction. Now convection, how do I stop convection? Let's say I had my cup and it's got hot water in it, and the hot water is heating up the air and the air is leaving, taking its thermal energy with it. How do I stop that thermal energy from leaving my cup? Right? Well, because it's the motion of the air, the motion of the hot pack of air that actually is pulling away the energy. Here's how you stop convection. You just put a lid on it. Right? This is why those reusable coffee cups, or any kind of coffee cup, will have a lid. The lid stops the convective heat transfer, that hot pack of hot air just leaving and taking its energy with it. It traps the hot air in there, and then the hot air and the hot coffee is going to exchange energy by conduction, staying warm. Right? Now radiation is light. Radiative heat transfer is a light wave. We can't stop radiation. Right? And remember to keep in mind up here, everything radiates. There is no way to stop something from radiating except for to let it get colder. Then it'll radiate less. So we can't stop it. We can't prevent radiation, but we can bounce it. We can bounce it with a mirror because mirrors bounce light. So we can bounce radiation back. And that's where you see these like marathon blankets that they give to marathon runners and stuff, and survival blankets. What they do is, your body is producing that infrared radiation. It's just taking that and bouncing it back into you. And then so the radiation comes out, comes back around, and hits you. It's almost like an echo. Like think about like a sound echo, but it's like a light echo. And then it vibrates your particles right back, so you get warmer. So theoretically, if you had one of these, you would actually be mostly invisible to one of those infrared cameras. Because it's not letting that radiation out from itself, it's just keeping it in on you. And it's the hardest thing to stop completely. We can't stop it at all. We just have to return it back. That's why when you have one of those coffee cups, it's usually like a white or a silver inside, so then the radiation comes out and it just bounces right back in. This is why we have layers in the winter. We have layers in the winter because we put layers of air between us and the environment. Layers of air between us and the environment. So layers of air stop conduction, will slow down conduction. The fact that it's a wall will stop convection. sometimes these things will have a shiny kind of surface to send back the radiation as well. Yeah, so that's kind of interesting. So here's a task for you guys. It'll be to explain how the design of this thermos prevents all three methods of heat transfer. And I'm gonna do this in the actual class. I've actually got a thermos that I'm going to show off for you guys, and you'll have to explain to me how each of these three methods of heat transfer get stopped by that thermos design. Yeah, that's it for today. I'm gonna save the rest of this, different materials at the same temperature and different states of matter at the same temperature for tomorrow's lesson, because this is kind of complicated enough to understand on its own. So check for the quiz on EDSB, and I'll see you guys in the live class. Thanks.